Hi guys, my name is Anaga and today we're going to be talking about the binary numbering system. So for your reference, we will be following the information in the textbook, An Invitation to Computer Science, second edition. Well, mine is the second edition, but you can use any edition you want. Any quotations are from that book, and it's a great textbook. I definitely recommend it. It's what we used in my AP CSP class, and it's a really good textbook if you're interested in getting a good introduction to computer science and how computers work. So what is the binary numbering system? So in case you guessed, computers don't use the same numbering system as we do. We use the base 10 numbering system and computers use a base 2 numbering system. I'll be going into depth about the difference between those two in the next couple of slides. So what numbering system do we use? As I said earlier, we use the base 10 numbering system. And I think you guys will get a good feel for what this means in this next example right here. So 531 equals 5 times 10 to the power of 2 plus 3 times 10 to the power of 1 plus 1 times 10 to the power of 0. So we can see that everything is kind of 10 to the power of something, right? And this is like a really good numbering system, I guess, and it's what we use in everyday life. I'm sure you guys know that. It's like in case like when you were younger, in case you guys have used those like I remember in elementary school, like in my school at least, we had those like small blocks, and then you had for ones you would have like a cube, and then for tens you would have like a stick made of 10 cubes, and then for hundreds you would have okay, well you get my point. But like I guess that is a really good way of understanding our numbering system. So computers don't use that same numbering system. They use the binary numbering system. So binary means 2, and that's referring to the fact that we're using base 2 instead of base 10. So you can see here in this example right here, 1001 equals 1 times 2 to the third plus 0 times 2 to the second plus 0 times 2 to the first plus 1 times 2 to the 0. So it's pretty straightforward in terms of how to kind of read and understand that. And if you kind of add those numbers up, you'll get a number like, I don't want to do the math right now, but if you add that up, you'll get it in like base 10. And the binary numbering system, as you can tell, consists of zeros and ones. Like this number right here, 1001, all the numbers in a binary number will be a 1 or 0. So why do we need this new numbering system? Why can't we just stick with base 10? So I think this quote from the textbook that I mentioned earlier is a really great explanation for why we do use base 2 and binary instead of base 10. So I'm going to read it right now. Binary representation is used exclusively, not for theoretical reasons, but for reliability. Computers store information using electronic devices, and the internal representation of information must be implemented in terms of electronic quantities such as currents and voltage levels. Building a base 10 decimal computer requires finding a device with 10 distinct and stable energy states that can be used to represent 10 unique digits 0 to 9 of the decimal system. Electrical systems tend to operate best in what is called a bistable environment, in which there are only 2, rather than 10, stable states separated by a huge energy barrier. So as we can see from this quote, let's say we have a computer, right? And we want to figure out how to represent numbers. Rather than finding like 10 specific like voltage levels that would represent each digit, it's a lot easier if we just have 2 states, because we could literally just do on and off. And that really represents why we would want to use base 2 over base 10. Like as computers age, right, like your current and voltage levels aren't going to be as accurate as they were before. So it's really like we don't want a computer to become less accurate as it ages. So a base 2 numbering system is really helpful like for this specific reason. So how do we convert from one numbering system to another? I'm sure you guys are wondering that, because you're like, I know base 10, this new like numbering system, how do I convert between them? And no, you don't have to just grind it out and like try to like figure out the right combinations of ones and zeros that's going to add up. There's actually a really simple way. So you can so the problem here is convert 321 to binary. So we're going to be using something called the division method. So in the division method, you keep dividing your number by 2, and you keep recording your remainder until you divide by 2 and you get 0, right? Also, that 1/2 is supposed to be 1/2 divided by 2. I think it got cut off, but yeah. So then you like you note down the remainders that you have in reverse order, and you're going to get your number in binary. So in this case, 321 in binary would be 101000001. You guys can do the math if you guys are like not sure if I'm correct or not, and we can even check our answer. So I mean, if you really wanted to do this long way, you could do like 0 times 2 to the power of whatever equals 0, but I just kind of took the 1 digits. I mean, for practice, maybe it's better to just take 0 so you guys don't get confused, but essentially 1 plus 64 plus 256 equals 321. So we were right. Yay! Okay, so binary addition. So we have some binary addition rules that we need to follow in order to add two binary numbers. So there's four basic rules, which are 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals 10. So we're going to do like a practice question to kind of understand how this works. So we have this long number 101000101 plus 101010110. Okay, that was a mouthful, but basically you can see, for example, that I use my first rule here, 1 plus 0 equals 1. So we have a 1 right here on the left, rightmost digit. Then we have 0 plus 1, which equals 1, based on the rules we have. 1 plus 0 equals 1, 0 plus 1 equals 1, 0 plus 0 equals 0. But then we have 1 plus 1. This is kind of where things get tricky. So we have to carry the 1. As you guys can tell, I put 1 plus 1 equals 10, but it's not 10, it's 1, 0. So you would keep the 0 in that place value, I guess, and then you would carry the 1 to the next place value. I'm not sure if that's the right word, but I hope you guys understand like the next digit, and you add those. So 1 plus 0 plus 0 equals 0. So for example, if we had like 1 plus 1 plus 1, then you would have 11 instead of 10. And also, me saying 11 is wrong, but like you put a 1 for that place value, and then you carry the 1 for the next one. And then 1 plus 1 equals 1, 0. So that's how we get that answer. And we can check our answer too, right? You guys can either convert that binary number to a decimal value, and by decimal I mean base 10. You can convert that manually. I just used a binary calculator I found online. So we get the first number is 165, and the second number is 170, and the last number is 335 when I converted them after calculating it in binary, and that is correct. 165 plus 170 is 335. So now we're going to try a little bit of subtraction. So we have a different set of rules for binary subtraction. So 0 minus 0 equals 0, 1 minus 0 equals 1, 1 minus 1 equals 0, and 0 minus 1 equals 1 with a borrow. I also didn't mention this in the previous slide, but please don't mix up decimal operations with binary operations, because they are different. You do need to memorize these new rules. So let's take this example, 101,001 minus 101,000. Okay, that was a little easier to read than the last one. But 1 minus 0, as we can see, is 1. 0 minus 0 is 0. And 0 minus 1 equals 1 with a borrow. So we need to borrow from the previous digit. And to do that, we're going to cross out the previous digit, so it becomes a 0 technically. And then we're going to take two ones to that side. So then we get 1 minus 1 minus 1. So the two ones cancel, and then you have a 1 left, so you get 1. And then you have 0 minus 0, which is 0. You have to borrow again from the, okay, I don't want to say a place, but the leftmost value on the first number. And so you borrow from that, and then you end up with 1 minus 1 minus 1. And then two ones cancel out, and then you have a 1 again. So our final answer is 10101, and let's check it. So the first number equals 41, second number equals 20, and the last number equal to 21, and that is correct. 41 minus 20 is equal to 21. So yay, we solved that correctly. So before I kind of close off, I just want to make a couple of statements and stuff like that. So there are a couple of different numbering systems. For example, you have base 16, base 8. You guys might know of them, hexadecimal, octal, I think is what it's called. And those are all useful too, but for like to make sure that I don't confuse you and give you too much information in one video, I kind of stuck with binary for right now. And there's a lot of uses for binary, which we'll go over in future videos. But I hope you guys have an intro to binary and binary operations and what binary is used for through this video. I'd like to say a special thanks to Slides Go for making my presentation pretty, because I suck with like presentation slide thingies. And so, thank you. And thank you for listening to me talk about zeros and ones for I don't know how many minutes this is, but yeah. Thank you. Bye. See you next time.